Thank you. And thanks for the very kind introduction. Much appreciated. It's great to be back in Aspen. This is a really special place. I always love coming here. And the Aspen Center for Physics is a true gem, world famous, and you're really lucky to have it here. It's a really remarkable place. I'll be talking about some profoundly mysterious questions we face regarding quantum mechanics, black holes, and space-time. And in outline, I'm going to start with some very short lessons. First, some of how quantum mechanics is weird, and quantum mechanics is weird indeed. Secondly, I'm going to talk about this notion of space-time and related discussion of how it's impossible, apparently, to travel or signal faster than the speed of light. Then I'm going to talk about the fact that space-time is dynamical. That's associated with Einstein's general theory of relativity. It explains gravity, and we'll briefly go over that. And then we'll turn to some puzzles and paradoxes which we face when we try to start combining some of these ideas. And the first basic question is, how do we describe space-time in the quantum context, the context of quantum reality? And a way of testing some of our ideas is to think about the extreme arena of black holes and their physics. And when you do so, we actually encounter a crisis, which is really telling us there's something profoundly wrong in our understanding and is suggesting new paradigms in the basic description of reality. And so this is really starting to get us in the direction of some hints for new foundations of physics, quite possibly involving some new black hole behavior beyond what I'm going to initially tell you, and a hint of what quantum space-time might be. And then finally, I'll talk a little bit about the possibility we might obtain observational hints on these subjects using some of the new ways that we're observing black holes in the cosmos. Let's start out with quantum mechanics. Like I said, quantum mechanics is really weird, and I'd like to contrast what we think with, which you might describe as classical physics, with quantum reality. So just a little demo. Maybe someone can help me out. Just want you to catch this tennis ball and throw it back to me. Worry, it's not a trick. It's not a quantum tennis ball, or maybe it is. So, you mind? Can someone help me in the front row? Maybe. Okay. Throw it back. Good. Okay. Somewhere over here. Is someone willing to catch? Okay. Throw it back. Okay, so everyone knows how tennis balls behave. But if we were talking about electrons, the world is very different. So this is a similar experiment where we imagine sending electrons towards a screen with two slits in it. And then there's an image screen on which we measure the number of electrons that come through. We see this striped pattern. Higher density of electrons or lower density. Where does that come from? Well, that striped pattern is telling you that unlike the tennis ball, if I threw an electron, it goes through both slits and reaches the image screen. It's as if this were an electron, it would both to you and to you came back to me. Both at the same time. That is quite strange. How can we understand that? Well, this is the kind of behavior we see with waves. This kind of pattern comes from wave behavior. You can think about, say, water waves, which this might illustrate, where you have a source of waves, and then the waves propagate to the two slits, and then they fan out from the two slits. And you get, so to speak, interference between the water waves. Some places, one wave is going up and the other is going down, or some places they're both going up. So you get this striped pattern from the interference of the water waves. This is an experiment you could do. Just throw two rocks into a pool of water and watch how the ripples combine. And so the electron is somehow having this wave-like behavior. The really weird thing is that each electron, like each tennis ball, goes through both slits, make this pattern. And here's a simulation of that behavior. If you let electrons go through one at a time, you gradually build up this interference pattern. And this is telling you that in some sense, each electron is going through both slits. It's very strange. And here's an actual, not just simulation, but experimental example of the buildup of this kind of interference pattern over time. So quantum objects are quite strange. This doesn't just hold for electrons, which, by the way, of course, the electron is one of the basic constituents of the atom, but it holds for much bigger things. In fact, this kind of behavior has been tested for objects as heavy as 25,000 hydrogen atoms, big complicated molecules. In principle, this kind of behavior governs tennis balls, though in practice, that's not something you can measure for tennis balls. So this is part of the basic description of reality. And the fundamental thing in physics is not particles moving on trajectories like tennis balls. It's something else. It might be described as the quantum field of the electron travels through both of these slits and then reaches the image screen. It follows both paths, and it doesn't behave anything like what we might have expected for, from our familiar objects like tennis balls and so on. The quantum structure of reality is very different. Okay, so that's a first lesson. Next, let's turn to another interesting question. Why can't we go to or send a message to Alpha Centauri, now? And that's something I'm going to explain by introducing the notion of a space-time diagram. We'll be using more of these. A space-time diagram is a diagram where space goes across and time goes up. So pretty simple. And so here we have the trajectory of Earth in space-time, which is basically in the frame of reference of the Earth, is just moving in time and not moving anywhere again in that frame. And let's think about the nearest star system, Alpha Centauri. If we want to send a signal to Alpha Centauri, well, if it's a light signal, then it's going to take 4.4 years to get there. And that's associated with the statement that the distance to Alpha Centauri is 4.4 light years. So the light signal follows this light blue dotted line. And since Alpha Centauri is 4.4 light years away, it takes 4.4 years for light to get there. And we actually more generally think about all of the light signals, say, emanating from Earth. So we might think about light signals going in other directions, and those form what here looks like a sort of just two dotted lines, but really it's kind of a conical structure if you look at all possible directions of the light cone. And the basic statement is that we can only signal or move within the light cone, so no faster than the speed of light. And so, for example, signals could travel, or objects could travel more vertically and take longer to get to Alpha Centauri than 4.4 years. They can never travel more sideways outside the light cone and take less than 4.4 years to get to Alpha Centauri. And that's true even when you take into account some of the strange quantum behavior we were just describing. There's other strange quantum behavior as well. But even quantum particles or fields don't change this story, despite some popular misconceptions. Right. The next lesson. Einstein taught us in his general theory of relativity that space-time is dynamical. It bends and it ripples. And this is, in fact, the current best way of explaining gravity. So if you think about the Earth, And the Earth creates curvature bending of space-time in its surroundings. And so that's what explains why satellites orbit the Earth. It's because they feel this bending of space-time. That's why the moon orbits the Earth. That explains gravity. You can't see space-time directly. You can feel it. That's what's causing the pressure between you and your chairs right now. You can feel that curvature of space-time. It gets more interesting. Let's suppose we have not just Earth creating a gravitational field. Let's suppose we have two very heavy objects, maybe two black holes or stars. Suppose they're orbiting one another. And that is going to change the curvature of space-time in a way that depends on where they are. And so, in general, we'll create a complicated pattern of ripples of space-time that goes out across the universe, across galaxies. And we have measured these ripples in space-time now, in the last 10 years, in these remarkable detectors. This is a picture of one of them up in Washington. They're around a mile long on a side. I won't go into the details. It's an amazing experimental feat, but basically it involves having two masses suspended, and one of these ripples comes along and it just moves these masses a little bit. How do you know it wasn't seismic activity or something like that? Well, they have a detector in Washington and one in Louisiana, and they have seen patterns of oscillation like that at essentially the same time. There's a little bit of time difference between when the signals arise, with the same pattern. So here we have in this graph superposed the pattern of oscillation in blue from one, the pattern of oscillation in red from the other, and they line up. This was the first signal discovered, this kind of ripple in space-time. And so that's really truly remarkable. We've seen not only that space-time is dynamical and responsible for gravity, but we've seen the actual, ripples in space-time from across the galaxies. An amazing thing. All right, well, let's try to put some of these things together and ask how we describe space-time in the quantum context. So in the classical approximation, what we're familiar with, you have particle trajectories like for tennis balls, but the more basic reality is what we might call quantum fields, which have this very strange behavior like going through both slits of a screen. That's the underlying quantum reality, very different. Now I've said space-time is dynamical, space sort of moves and ripples. What's the correct quantum description of that? That's going to be even more different from our usual expectations than, say, quantum fields are from particle trajectories. Now, just a small comment, you might say, well, maybe space-time doesn't have this quantum behavior. It stays classical, but everything else is quantum. There are people who are attempting to make sense of that story, but it's very difficult to do so. It looks like even bigger difficulties than some that we're encountering now. So I won't talk any more about that subject. This problem of combining these things is now a 100-year-old problem, now that quantum mechanics is 100 years old. And I think it's the deepest problem in physics. And so far, these two notions, space-time and quantum, clash in a profound way and really have been giving us a lot of trouble. So how can we start thinking about these subjects and get some idea about how we might combine the two? Well, one way is to take gravity to the extreme and think about black holes. So let me talk a little bit about what a black hole is, and I'm going to describe it in terms of a space-time diagram. So how do we get a black hole? One way is there are really big stars out there. Stars, are the matter in stars is pulled towards the center due to gravity. But stars are burning their atoms through fusion, And that creates pressure that holds stars up. Now, if you get a big enough star and it eventually burns all of its nuclear fuel, it's going to start to collapse under its own gravity. And long story short, there are more complications, but long story short, if it's a big enough star to start with, it just keeps collapsing under its own gravity and collapsing and collapsing and collapsing, and it doesn't stop. Here that's represented by the red line, collapsing star. Now let's think about objects that you might throw from the surface of that star if you were able to stand on that star. If you think about, say, a tennis ball and throw it up in the air at a certain velocity, well, it goes up a little ways and comes back down. But if I throw it fast enough, it will escape the gravitational field of, well, in our case, of Earth, or the star. If I throw it fast enough, it will escape all the way to the distant stars. And so that critical velocity, which I'm obviously not going to exceed here, is called the escape velocity. And the basic point is if this star keeps collapsing, eventually that escape velocity reaches the speed of light. And that's represented by showing propagation of these light rays. The so-called outward going light ray, once you reach that radius, isn't really outward going. It is moving through time, but it doesn't go further from the star. That's why the blue dotted line is going straight up. The inward going light ray goes towards the center of star, or whatever is the result of the collapse. It's sometimes called the singularity, but that's just saying we don't know. But that is the structure of the light cone once a star is collapsed this far. And that place where the outward going light rays are no longer outward going, called the event horizon, and once one of those forms, we have what's called a black hole. Since nothing travels faster than speed of light, roughly speaking, nothing gets out once you're past this point. And we have now seen this behavior through our observations. I'll talk a little bit more about this, but this is a really famous image that came out just several years ago of a black hole the mass of 6.5 billion times the mass of the sun in the neighboring galaxy M87. And the darkness you see in the center is directly related to this behavior that the light can't get out from the event horizon, or it's difficult to get out from the region very near the event horizon. So we're really seeing this behavior now directly through observation. And there are black holes of all different sizes. For example, the sun, if you were to compress it enough, it would form a black hole once it reached a diameter of around 4 miles. The Earth, you'd have to squish it down to about an inch. But in principle, there are all different sizes of black holes. They're possible. Okay, so that's black holes. Now let's talk a little bit about black hole evaporation. So this involves starting to combine some of the ideas of quantum physics with what I've just told you about essentially general relativity, Einstein's theory of gravity. And one of the other properties of quantum matter is sort of everywhere in space, and in this room and everywhere else, there are sort of fluctuations of these quantum particles into and out of existence. And that's what's represented by these little ripples. The thing is when you have the very strong gravity of being near the event horizon, basically that pulls these fluctuations apart, and you end up with an outgoing quantum particle and a partner particle which goes in towards the center of the black hole. And this is true for all different kinds of particles. It could be electrons, it could be photons, the particles of light, all different kinds of particles can be emitted in what's called this Hawking radiation. Again, I think this is Hawking's greatest discovery. I think many would agree. This changes the story of black holes in the sense that these outgoing quantum particles carry mass, they carry energy, And so they're carrying away some of the black hole's mass, and that means the black hole is going to shrink. And we can represent that, although I haven't pictured it here on the next slide, by the fact that the size of this horizon shrinks with time. After it's a lot of particles have to be emitted for significant shrinkage, but eventually, over time, a black hole will evaporate in this fashion. And this is what leads to our crisis in gravitational physics. And I refer to this sometimes as the unitarity crisis. It's also known as the black hole information paradox. And this problem comes out of, well, starting with the question, what happens to stuff that falls into a black hole? It's a basic question that kids first ask when they hear about black holes. When I first heard about black holes, that's the first thing, what happens to stuff that falls in? And that is a very interesting question. So let's first go back to our space-time diagram. We've got the evaporating black hole. We've got a huge number of, over time, these outgoing Hawking particles coming out. I've only shown 2. Eventually that leads to the black hole shrinking down to, in principle, it's almost a zero mass. And then the question is, what happens? What happened to the stuff inside? In some sense, the energy came out in the Hawking radiation, but is that all? Well, a sharper way to think about this is in terms of information. Okay, so